Alright guys, this is section 4.1. In this section our goal here is to be able to graph quadratic functions in standard form. A little bit of vocabulary. A quadratic function is a function that can be written in the form y equals ax squared plus bx plus c. So this is our general formula for a quadratic function. A parabola is a set of all points equidistant from a point called the focus and a line called the directrix. So these are U-shaped looking graphs for quadratic equations or functions. The vertex is the point on a parabola that lies on the axis of symmetry. It's either going to be the highest point or the lowest point of that U-shaped parabola. And the axis of symmetry is the line perpendicular to the parabola's directrix and passes through both the focus and the vertex. Right now we're going to focus mainly on the vertex and axis of symmetry parts of the parabola because the focus and the directrix will be talked about in later chapters. So when we first go to graph quadratic functions, we're going to make a table of values, then we're going to plot those points from the table onto the graph, and then we're going to draw a smooth curve through those points. So these are going to be smooth curves like a U shape, not a harsh vertex point like the absolute value functions had that looked like V's. So for example, if we wanted to graph these two quadratic functions on our graph, first I want to graph the parent function, which is y equals x squared, and then we're going to graph y equals 2x squared and compare that. Okay, so I'm going to graph this first one, y equals x squared. And we need to make a table for it. So we're going to make x values and y values. And some good x values to plug in every single time are -3 through 3. So if we start plugging those values in for x, we get back 9, 4, 1, 0, 1 again, 4 again, and then 9. So if we go ahead and graph those on the graph, -3, 9. And -2, 4. -1, 1. 0, 0. 1, 1. 2, 4. And 3, 9. And we're connecting them with a smooth curve. Okay, there's our parent graph of y equals x squared, but now we need to make a table of values for y equals 2x squared. Okay, using the same x values, -3 all the way through 3. Plugging those into that equation, we get back 18, 8, 2, 0, 2 again, 8, and 18. So if we go to graph these are going to start off the grid just a little bit. So -3, 18 I'll put up here. -2, 8. -1, 2. 0, 0. 1, 2. 2, 8. And 3, 18. And we're connecting those with a smooth curve. So here was my y equals 2x squared. So now if we compare these, comparing it from the red to the blue, this one is narrower. And they are both positioned at the origin and not really translated left, right, up, or down any. So here are our graphs of these two quadratic equations. Looking at the next example, still graphing the original parent function here. I'm going to go ahead and graph that again. So we had -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. So here was our parent function. Okay, but now we need to graph this other quadratic function here. And again, we're going to make a table for it. Okay, so if I make x values again, I'm going to do -3 through 3 again. If I plug -3 into this equation, I get back -1.5. And then if I plug -2 in there, I get back 1. And then 2.5. If I plug in 0, I get back 3. Then I get back 2.5. 1 again. And again, -1.5. So if I graph those, -3 and down 1.5. -2, 1. -1 up 2.5. 0, 3. 1, 2.5. 2, 1. And 3, -1.5. And I'm connecting those with my smooth curve. Okay, so right off the bat, if we compare these two, the blue one is reflected over the x-axis. Also, it is translated up 3 units. And it's also just a little bit wider than my red graph, or parent function y equals x squared. Those are the main comparisons here between these two quadratic equations. So building upon those characteristics, we have properties of quadratic equations. They're kind of like when we did absolute value equations as well. So if we have a graph that opens up, your A is always going to be positive. So open up meaning a U-shaped. But it's going to open down if your A is less than 0. So if it's negative, then it's flipped over like a hill-shaped. And if it's positive, it's the U-shape. If the graph is narrower, then that means your A out front was bigger than 1, and it was wider if it was less than 1. So like a fraction, that would automatically be a wider shaped parabola. The axis of symmetry we always get by this formula right here for x. Okay, and the vertex has that same x coordinate that we got from that little formula. And then if we wanted to get y, because the vertex is an xy point, all we would need to do is figure out from that formula for x and plug it back into the original quadratic equation to get y back to help us make that vertex. And finally, the y-intercept is always your c. So the point 0, c is on the parabola, and it's the y-intercept, or where it's crossing the y-axis. And always in a quadratic equation, you're always going to have a with the x squared term, b with the regular old x term, and your c, or constant tacked on the end, will be the c. So knowing this info, let's try to graph this last example here for the graphing. So if I want to graph this, first I want to think about some characteristics about it. So since I don't see any negative signs, I know it opens up, kind of like that U-shaped that we talked about. Okay, since there's a 2 out front, it's going to be more narrow. Okay. Then I could start thinking about what my axis of symmetry might be, and we got that by doing that little formula for x, or -b over 2a. So if I figure out a, b, and c, well, a is always with my x squared term, b is always with the regular x term, and c is always the constant on the end. So if I plug those in for b and a and simplify, that gives me 8 over 4, which is really 2. So I know my x value is 2, and my axis of symmetry starts out with 2. So my vertex is 2, but I said, well, in order to get my y value, I needed to take that value of x and plug it back in to the original quadratic equation. So I'm going to do that here. Okay, so if I do that, 2 squared is 4 times 2 is 8, minus 16 here, which is negative 6, or negative 8, excuse me, plus 6 is negative 2. So here's our negative 2 y value. Then lastly, if we need a y-intercept, again, that was just our constant with a value of 0 for x because it's lying on the y-axis. And in this case, our c was 6. So there is our y-intercept. So now we can actually start graphing what we already know. So at 2, negative 2 is our vertex. We also know the y-intercept is at 0, 6. And we know our axis of symmetry is running down through x equals 2. And I'm going to make it a dotted line because it's kind of like our symmetry line here for our parabola. Okay, I only have 2 points, so if I make one more, I'm going to reflect our y-intercept over our axis of symmetry line. It's kind of like a mirror. So my y-intercept was 2 units away from that axis of symmetry line, so I'm going to go 2 more units to the right of the axis of symmetry line, and that point will be 4, 6. And all I need to do now is connect them with my smooth curve and make sure it agreed with my characteristics I thought it was going to look like. So it's opening up, that's good, and it's more narrow, that's good, and I have all my points plotted where they needed to be. So a little bit more vocab here. We have that a minimum is the y-coordinate of the vertex for a positive quadratic function. So minimums, if your a is greater than 0, then it's going to be looking like a U-shaped parabola. So those are the minimums. So think of you're like on a roller coaster and you're going down, you're at the lowest point and then going back up. That's your minimum point. The maximum, on the other hand, is the y-coordinate of the vertex for a negative quadratic function. So if your a is less than 0, so if it's negative, then these look like hill-shaped parabolas, okay? And like if you're on the roller coaster, you're at the highest point up top and then you're ready to go back down. That is the maximum point or maximum height before you start to go back down. So if your a is negative, that is the maximum. So our last example here, we're going to tell whether this function has a minimum value or a maximum value. And then we're going to find that minimum or maximum value. Okay, so anytime you see the words minimum or maximum, you should be thinking that you need a vertex. Because no matter if you have a U-shaped or hill-shaped, right, you're looking at the point of lowest or highest on your parabola, which is always going to be that vertex. So we're going to have to find the vertex here in a second. But if I need to tell whether this is going to be a minimum or maximum, again, I'm looking here at my a value. Okay. Since my a, in this case, is bigger than 0, or 3 is bigger than 0, this one is going to be a minimum. Okay. So we do have this sort of U shape here. And we're going to try to figure out that vertex or the minimum value. So how I do that is by taking that x formula, negative b over 2a, and plugging in what I know. Well, I know b and c because we just did a. So b is already negative right now. So I need 2 negatives in there. And my a was 3. And if we simplify that, that really is just 3. But now I need the y value. So again, to get the y, I'm just going to re-plug that back in. Okay, so if I do that all in the calculator and simplify that, I should get y equals negative 7. So my minimum value, or my lowest point on my parabola, that y value is negative 7. Because my vertex was 3, -7. And that's all I needed because it was a minimum, and I found that minimum or maximum value. So anytime you see a minimum or maximum and you need to find its value, you're always going to be taking a vertex.